I appreciate you being here. My name is Artur. I'm an information security engineer. I work at Google in the Zurich office. As an information security engineer, my focus is not to build, my primary focus is not to build new applications or systems, but to make the data that Google users have across our hundreds or even thousands of applications secure. And the way we do this is by building new frameworks and new platform features that we then adopt across all of Google. And this is what I want to tell you about today a little bit. I want to introduce several new features that are going to make their way into the web platform to be adopted by web browsers so that you can use them in your web applications to make your applications or your open source projects secure and prevent or mitigate the impact of some of the major vulnerabilities that have affected the ecosystem in the past. But before we can talk about the defenses, it helps a lot to understand what the landscape of vulnerabilities is, right? We have to start with the attacks so that we know what we can defend from. So this talk is divided into two parts. In the beginning, I will spend a little bit of time telling you about what the security issues are that the Google security team and the ecosystem is struggling and dealing with. And then I will tell you a little bit more about the exciting new defenses that we can all start using across our web applications. So let's get started. How do we know what kinds of vulnerabilities exist in applications? So at Google, we've been running vulnerability reward programs, which are initiatives under which we pay external researchers, developers, anyone who finds a security vulnerability in Google, any of our applications or any of our, the products that Google is building can receive a reward for their finding when they disclose it to us. We've been doing this for over 8.5 years. We have 3 major reward programs. There's one for Chrome, one for Android, but the one that I will focus on today primarily is what we call the Google VRP. This is the reward program that covers pretty much every Google application that users would interact with, like Gmail or Maps or hardware devices, Android applications like Google Docs or something that you might have on your phone, Chrome extensions, and so on. And under that program, we pay a little over $1 million of rewards per year, roughly, for hundreds of security flaws that researchers report to us. So based on that, we have an interesting data set of the types of flaws that affect Google applications and by extension, the industry. Because the vulnerabilities that we see at Google are not just in core Google applications, but also in our acquisitions. So hundreds of companies that Google has bought, which are built on different frameworks, different stacks. So we kind of get an overview of the types of bugs that are out there. So what are those bugs? That's kind of the interesting question. So first, those of you who are on this side of the audience can probably see the left side of the chart. For those of you there, I'm sorry, but I can tell you what they are. So there is, on the left side of the chart, there are vulnerabilities that are not related to the web. Those are direct bugs in server-side logic, in authorization, authentication, in hardware, and pretty much everything that is not related to the web. But if you look at the right side of the chart, you'll notice that more than half of the rewards that we've paid out over the past year and also over the past decade has been for web vulnerabilities. So those are issues that affect users who are logged into Google in their web browsers, and they allow certain kinds of attacks that I'll tell you about in a moment. But the thing for us is that these endemic web vulnerabilities are the majority of both the reward amounts and also, if you count the number of bugs, high-risk bugs, or just security vulnerabilities that exist in Google applications, the majority of them are these web issues. So we can roughly divide these web issues into 2 different classes. The first one is cross-site scripting, which you might know as XSS. In general, the idea is that an attacker might be able to inject their own scripts into the context of your application. And cross-site scripting is unfortunately very easy to introduce when you're writing your front-end code. So you see on the slide 2 examples of how XSS commonly happens in our applications. So the first one is if you render some content on the server, right? You have a template and you render an HTTP response that has HTML. If you include any data that is taken from the HTTP request or controlled by the user, then this is one way in which cross-site scripting can happen. The second common way is if you use any of a number of dangerous JavaScript functions that allow script execution, like inner HTML. It's also very easy as a developer to unwittingly introduce XSS. So if you have any of these patterns, and there are many other ways in which can happen, those are the 2 main ones, but we know at least a dozen different types of cross-site scripting that all have the same effect. And the effect is that if you have any of these patterns in your application, what an attacker can do is if a user is logged into your website, right? Let's say you have a banking website, a user logs in, what the attacker can do is they can direct the user, when the user goes to an attacker-controlled site, the attacker can redirect the user to your application with what we call a cross-site scripting payload. It's a bit of HTML that will get injected into the context of your application in your user's browser. And when the user's browser renders that bit of HTML, it will think that this is a script coming from your application. And that script will get full access to all the data that the user has in your app. So it will be able to read your cookies, your local storage. If the user has given your application permissions to anything like geolocation or anything else, the attacker will get access to that as well. And essentially the attacker will be able to act as your application and read or modify all of the data that the user has in your app. And that's kind of bad because these issues are very easy to introduce as a developer, but also very damaging. So this is the first class of bugs that we see. The second, much more diverse class of issues is based on the fact that there is no inherent isolation between web applications. So there are many, so unlike cross-site scripting, there are a number of different types of attacks on web isolation. They have different acronyms that security people are very excited about and love to talk about. As developers, you don't really need to know the details of these attacks, but I'll illustrate one that you might have seen in the past, and that is cross-site request forgery. So if you have a form like the one on the top of this slide, this can be a simple form where I as a user would see and would let me transfer $10 to my manager Jim. And this is perfectly fine, right? Like if an application has this form, I submit it, the transfer happens, and everything works. The problem is that an attacker can create an exactly equivalent form that points to our application server with data that the attacker controls, right? So the attacker can modify the recipient of the money to their own account. Instead of $10, they can say infinity dollars or a large number of dollars. And then when I, as a user, visit the attacker's site, that form can get submitted automatically to the vulnerable application server. And the application server that processes this form has no way of knowing that the request, of distinguishing these 2 requests, the legitimate form submission and the evil form submission. And this requires us to add special tokens anytime you submit a form to let your server distinguish between a legitimate and a potentially malicious form. So you have to have, for every form on your site, you have to do something special to protect it from being abused by an attacker. And the underlying cause of this is, as I mentioned, the fact that the server doesn't know, cannot tell these 2 requests apart, right? Because when the attacker submits the form to your server, that form will come with all of the user's cookies because the user is logged in. And this is just one example there are other types of vulnerabilities that rely on the same principle. There is no inherent isolation between applications. This leads to the attacker being able to send authenticated requests to your application server from their evil site. And it's very easy to confuse our application servers to essentially respond to an attacker's request with some legitimate data, which allows the attacker to leak information from our site. And you might think, oh, this is, maybe this is just something that Google is dealing with, and this is not a problem that we have across the industry. But if you look at the data published by other companies that also look at the sources of security vulnerabilities across the industry, you'll see very similar patterns. So this is data from HackerOne, which is a bug bounty program, which has, I think, thousands of customers, and they also publish some analyses on the types of vulnerabilities across these customers. You might not be able to see it very well. These are the top 6 classes of vulnerabilities in the HackerOne ecosystem, and you can see that it's the same classes of issues that we have at Google. The ones in the solid ovals are the, let's say, pure web vulnerabilities. The ones in dashed ovals are the ones that could be web or not. But the majority of the most frequent sources of bugs on HackerOne sites are also web issues. And this is data that comes from our friends at Mozilla. They've also published some information about the sources of issues on Mozilla sites. The huge bar on the left side of the screen is cross-site scripting. The other ones marked in red ovals are also the endemic web vulnerabilities. So clearly we as an industry have a problem with web bugs, with these 2 classes of injections and lack of web isolation. So in the remainder of this talk, I will tell you about 4 new web platform features that we all can use to protect our applications, divided into 2 groups, which are injection defenses and ways to give your application some isolation primitives. But before I get there, this is a good time to pause and see if anyone has any questions about these vulnerabilities or the attack side of issues. And if not, I will just move on to the defenses. So I'll give you a moment to see if no one has questions. Great. Okay, let's talk about the defenses. So the first protective mechanism that I want to tell you about is content security policy. Content security policy is a generic browser mechanism that lets you enforce restrictions on what your application is capable of doing. And by enforcing these restrictions, you can prevent injections from allowing the attacker to execute malicious code in your application. So the 2 main things that content security policy lets you do is control scripts and control plugins. So you can say, these are the scripts that I will allow the user's browser to run when they are on my site, and these are the plugins that I will load. And it's important to note that content security policy is not a silver bullet. It's a defense in depth mechanism. You should still do all the usual security things. You should escape data that comes from users. Try to make sure that your site does not have vulnerabilities in the first place. That's obviously ideal. But if you do have these vulnerabilities, and as you saw, they are very common despite our best efforts, content security policy can save you. So how can it save you exactly? Let me show you. So the first thing to note is that CSP is a HTTP response header. So you can define a header, set a header in responses from your applications, and that policy will be interpreted and observed by the user's browser. Pretty much every modern browser has some support for content security policy. Not all of them support the most recent version of the spec, but it's good enough and it's getting there. And there are two modes in which you can configure CSP. The first one is enforcing mode. So if you just set the content security policy response header, that will enforce all the security restrictions. But before you do that, you can also set CSP in report-only mode, which will not affect any of the behavior of your application, which means that it will not break anything, but it will tell you if there are any incompatibilities once you enforce CSP. So this is something that pretty much every website that wants to start using CSP starts with. So you start with report-only mode, and then you move on to enforcing these restrictions. So can I get a show of hands if you have seen or used content security policy in the past? Can you raise your hand? Okay, great. There's several people. If you have used content security policy in the past, you likely had to configure a policy like this, which, please don't try to read that slide. It was a nightmare. It's very, very difficult to get right. It was very verbose. This is not what I want to tell you about today. I want to tell you about the modern way of adopting content security policy. And the modern way is this. We call this nonce-based CSP. So the idea here is that you set a policy that is very short. It's always the same, save for, so in computer security, a nonce is a number used once. So this is it's a value, a random string that you have to change for every response. So you will set a policy like this with a nonce value that changes for every response that your server issues, and then you'll have to modify your application to conform to the policy. So, and what happens when you set a policy like this is first you have to set the header. And what the browser will do when it sees that header is it will require every script that is present in your application to have an attribute with the same value that was sent by the server in the response header. So if the browser sees a script tag that doesn't have a nonce attribute that is the same as it thinks it should have, it will just block that script. That script will not execute at all. And this is a way to block injections that are controlled by the attacker, because the attacker, even if he or she can inject markup into your site, they will not know the random number that's required for a given response. So they will inject a script, but that script will just be blocked by the user's browser. And legitimate scripts all have to have a nonce attribute that is interpolated by your template system that matches the same value that was sent by the server in the response header. The difficulty with this way of deploying a content security policy is that for every script that your application is loading, you have to attach the correct nonce attribute to that script element. And this is easy for things in your HTML where you can just add that attribute. But it's a little harder if you have any dynamically loaded script dependencies. For example, if you use third-party JavaScript libraries, or if you just dynamically load code. So this has been a bit of a pain point for this kind of CSP deployments. But luckily in CSP version 3, which is the most modern and also fairly widely supported version of the spec, there's this new keyword which makes this way of deploying CSP much easier. This keyword is called strict dynamic. What it does is it requires the nonce to be present on every script that is in your markup, so every script element with HTML brackets. But when you load a script dynamically, for example, when you call document create element and then you load a script at runtime, that will be allowed to execute. And this is because the script that you've already allowed to execute with a nonce attribute is trusted. We know that it comes from your own server. It has the right value, so the browser can say, okay, I see a script is being dynamically loaded by an already trusted script, so I will just load it. It's fine. And this makes deployment much easier because the only thing you have to do is to make sure that your script elements have the right nonce property. So let me show you with some examples the process of adopting this, this cross-site scripting protection and adopting nonce-based CSP. And it's divided into 3 relatively simple steps. So the first one is there are some patterns that are not compatible with CSP. For example, inline event handlers and JavaScript URIs are ways to execute scripts without a script tag. And you cannot really have these in your application, so first you have to refactor them into a format that will be, that is compatible with CSP. So for example, if you have an inline event handler, you can, instead of defining it as an on-click attribute, you can at runtime add the same handler from a script element. Similarly, if you have a JavaScript URI, you can either use the first method, so you create a script element and attach an event handler to the link element, or in many cases you can also just, especially for this pattern of void zero that was often necessary for backwards compatibility on link elements, you can use, you can just remove the JavaScript URI in the first place. Okay, so that was the first thing. We have to remove these blocking patterns that prevent us from adopting CSP. And then the main thing to do is to configure our template system to interpolate the correct nonce value into our script elements. So if you use HTML templates like Django or other modern templating systems, you just modify your templates to inject that property. You give the template system the value that you put in the content security policy response header, and you are pretty much done. And at that point, you are, you're very close to having a policy enabled in your application. The last thing you have to do is enforce CSP, right? So you've done all the refactoring work, you've removed these patterns that are incompatible with CSP, you've refactored your templates to add nonce attributes to script elements, so now you just have to set the header. And there are 3 different ways in which you can set the header. The first one is what we usually start with at Google. It's a slightly more permissive policy, which is easiest to adopt. And then we can progressively make it a little more, a little stricter. So we can remove some of these keywords that, for example, allow the use of eval and allow the loading of dynamically loaded scripts. But even the first policy here is something that we are very happy with, and that has, over the past year, blocked around 25 high-risk cross-site scripting vulnerabilities across Google. So we've been using this technique very successfully across our ecosystem. And a few other things, because the things that I was talking about, they work for the big applications that we have. If you work on a smaller application, maybe you have slightly different patterns. For example, if you do not have an HTML template system, but you have a single page application, or an application that is static, instead of using nonce attributes to allow scripts to load, you can also use hashes. Hashes essentially identify the contents of a script and tell the browser that a script with a signature that matches the hash in the response header will be allowed to load. So this is equivalent security-wise. In some cases, it's even better. So if you have a site with static HTML that doesn't use an HTML template system, this is a preferable way of adopting CSP. You can also use the report sample keyword, which will give you more information about which parts of your site might not be compatible with CSP. And this makes it much easier to switch from report only to enforcing mode when after you've refactored your site. And finally, you usually need some fallbacks for older browsers so that the policy doesn't break functionality for users of browsers that don't have CSP. You just have to remember to do it. It's not a complicated thing to do. All right, so that is a fair amount of information. If you're looking for a more detailed guide about how to do this in your application and protect from XSS, you can go to cspwithgoogle.com. We also have this tool called CSP Evaluator, so that if you're ready to enable a policy in your application, you can just paste it into that tool, and it will tell you whether the policy is safe and whether it needs any fallbacks for backwards compatibility, and generally help you craft a policy that will make your application safe. Nonce-based CSP is much, much easier to adopt than previous versions of content security policy. If you've considered in the past adopting CSP, please use this technique. It'll make your life much, much easier, and it will make your application much more secure than it would have been with a previous version of CSP. All right, so mitigating bugs is great, but maybe we can do something even better. Maybe we can prevent vulnerabilities from existing in the first place. And one way to do this for a large subset of injections is called trusted types. It's this new browser API that lets you protect your application from DOM-based cross-site scripting. DOM-based cross-site scripting is the type of cross-site scripting flaw that arises when you use a dangerous JavaScript function, like you saw in the example at the beginning. So if you have some code that reads data that is controlled by the user, for example, it's part of the URL or it's part of user data that you've stored in a JavaScript variable and returned from the server, if you use that data in, for example, inner HTML, it will allow the attacker to send the user to a URL like you see on the bottom, and that part of the URL will make it into an inner HTML assignment, and the attacker will be able to inject markup into your application with the same effects as we talked about before. So the problem is that protecting your application from DOM-based cross-site scripting is super hard, because there are around 60, and we've counted all of these APIs across all browsers, there are around 60 major browser APIs that allow this bug to happen if you use this API and pass it untrusted data. So inner HTML is one, document.write, window.open, some of the functions that we all use a lot in our applications are dangerous whenever they get past untrusted data. So it's very, very easy to introduce this class of bugs. So what can we do about this? The problem, the underlying problem in all of this is that all of these APIs currently, in the current shape of the web, accept strings. So a string can be trusted data or potentially user-controlled data, and we don't really know from the type of the variable whether it's trusted or not. So the idea of trusted types is to require a special type, a special object type in JavaScript for any of the assignments into dangerous DOM methods. This is based on a technique that we've used internally at Google in the Google JavaScript ecosystem that has been super successful at eliminating these bugs. And now it's being moved to the web platform. So it's something that the browser will either natively support for modern browsers, or that you can use via a polyfill. So in somewhat more detail, how does it work? So first you would add a header that will make the browser enforce trusted types restrictions. It's currently the content security policy header, but this is, let's say, an implementation detail. You just tell the browser, hey, please enforce trusted types for my application. And then when you do this, the browser, when it sees a string assignment to a dangerous JavaScript method, it will just reject it. It will throw an exception and it will just not go through. So if an attacker controls the string, that will just stop working. But if you assign a trusted object to that API, that will be allowed. And something very similar is also available in reporting mode. So if you want to test if your application is going to work well with trusted types, you can enable it in report-only mode. And then when the browser sees a string assignment to one of these dangerous APIs, it will generate a report to your server, and your server will learn that this is something that needs to be refactored before you start enforcing the restrictions. So now the question is, okay, we know that you can you can pass these trusted types object to these dangerous DOM APIs and everything will be fine, but how do you actually get those objects? How do you create them? This is the kind of meat of the proposal. And the way to do this is that you use the trusted types API that the browser implements to create values, to create objects that are of the correct type. So in here, for example, you can see the create HTML method that you would define can be used to return objects that will sanitize some of the markup that might be in its input. So you can use something like DOM purify or any other technique that will make the markup safe from injections. And you then, once you've defined the create HTML method in your policy, this will create and return to you the trusted type, and then you get an object that you can assign to inner HTML like you could before. But it requires creating that policy and defining methods that create safe objects. And then you can enforce it with the content security policy header. The one other thing that is very interesting about this proposal is you can also define a default policy. A default policy is something that will run even if you if you don't have a trusted object that you pass to a dangerous JavaScript API, and that lets you do some logging that's, let's say, a stopgap. If you still have code that you don't fully control that passes strings to these dangerous APIs, the fallback policy, the default policy can let you make these assignments safe. So what does all of this do, right? Like, why is doing this good for your application? The main thing about this is that instead of needing to audit your entire code base for the use of any of these APIs, any of these 60 dangerous APIs, you guarantee that only the code in one of your trusted types policies can introduce vulnerabilities. The rest of your application, once you enforce trusted types, the rest of your application becomes magically safe from DOM-based cross-site scripting. The only places that you have to audit, that you have to pay attention to when you code JavaScript are these policy snippets. Because if your policies are safe, then there is no way for any of your developers that's working on your application to introduce this vulnerability. So you go from, let's say, hundreds of thousands of lines of JavaScript that your security team or that you have to review to make sure that these bugs don't happen, to maybe hundreds of lines of JavaScript. And this is really a very large reduction in attack surface. Currently this API is still in development. There's a polyfill that you can use and experiment with, and I would encourage you to try it out. So, all right. And there's also a lot of documentation that you can see with details about how to use trusted types. So a quick summary. The way that we are likely to improve web security over the next few years is by using these two techniques. We will use trusted types to protect JavaScript from DOM-based cross-site scripting, and we will use nonce-based content security policy to block any of the remaining server-side cross-site scripting issues. And the beauty of it is that you can just set one header, one HTTP response header, and that will enforce these restrictions in your app. So if you're starting to write a new app, this is something you can kind of lock in that security from the get-go, and you will have these security properties enforced forever for your application. All right. But that was only the first part. It's what we deal with at Google a lot, but this is not all there is to know about new web security features. The second class of issues that we talked about is due to the lack of isolation. So let me show you some examples of these lack of isolation, of these attacks that are due to the lack of isolation. So the first one is what we saw earlier. This is the attack based on the fact that a malicious site can make requests to your application that will come with your application's cookies, and then it might be able to infer something about the result. So it might either cause a state-changing action in your application, which will lead to cross-site request forgery, or maybe the response from your application, which is authenticated with the user's credentials, maybe the response from your application will make it into an attacker-controlled document. And once it's in an attacker-controlled document, the attacker can usually infer some information about it. For example, if you've heard about Spectre and Meltdown, those are some new, fairly dangerous attacks that allow leaking data from other sites in this scenario. The second way in which an attacker can bypass some of the security restrictions on the web and bypass isolation is by opening a window to you. And you would think, oh, if the attacker opens a window to my application, they shouldn't be able to really do much just because they opened that window. But I'll show you in a moment there are actually fairly interesting things that an attacker is capable of then. And finally, this is one last concept that I wanted to introduce to you before discussing the final two security mechanisms, and that is the concept of an origin versus site. So the browser considers two URLs to be same origin if they come from the same host, scheme, and port. And that tells the browser that two URLs that are same origin essentially share the same security principle. They are considered by the browser to be the same application. If two URLs or two documents are not same origin but come from the same domain and from the same scheme, they are considered same site. So the browser assumes that there is some trust between them. For example, they can share cookies, but there is no full access between those two documents. And finally, if a document is not same origin or same site to another document, then it's considered to be cross-site. All right, so let's talk about the security mechanisms that can give our applications some isolation capabilities. The first one is called Fetch Metadata Request Headers, and what they do is fairly simple. Fetch Metadata Headers annotate every request that a web browser is sending with some extra information, extra security information that gives the server, that allows the server to accept or reject the request based on that data. So these headers will tell the server which site generated the request, what type the request is, which is, it's called SecFetch mode, and whether there was a user interaction that led to the creation of that request. So it's best to show you an example of this. In the first one, this is just our own site that uses the Fetch API to download a JSON file. And the one on the bottom, it's an attacker's document that makes the same request, the request to the same URL, via an image source. Maybe by loading it as an image, the attacker can leak some data from our resource. So in the past, these two requests would be indistinguishable, but with Fetch Metadata, the server will get information about whether the request was made by our own application or by an external application. And that lets the server reject it if the server wants to do that. So this is a very small example of middleware that lets you enforce restrictions based on the values of these headers. So first, if there is a request that doesn't have any of these headers, we can just allow it to go through. This is what we call in security fail open. It is not secure, but it will allow our application to work in older browsers that don't support the specification. The second one is we allow all requests that come from our own site. And if requests don't come from our own site, but are simple navigational requests, we also allow them. But any other request, a request that is cross-site, that is not a navigation will be rejected by this middleware. So this is a very simple mechanism, but the server can create very powerful logic that will prevent its responses from being abused by an attacking site. And the process of adopting fetch metadata headers is kind of simple. First, you will monitor your application to see if you have any cross-site requests. If you do, you might have to exempt them from your logic. If you have any endpoints, any code that needs to be accessible cross-site, you can disable these restrictions, but enable it for all other parts of your site. And then after you're satisfied that you've that you're not introducing any breaking behavior to your site, you can enforce it and you're done. And there is some middleware that you can use if you want to try these restrictions in your application. And it's very simple, but it works. All right, I think I'm running out of time, so I'll very quickly tell you about the last mechanism that is that completes the set of features that will block the attacks that I started talking about at the beginning. So the feature is called cross-origin opener policy. And this is a way to protect our windows from being interacted with in a way that we don't want to allow. So the problem is that when an attacker can open our site in a new window, what he or she can also do is interact with our window. For example, the attacker can send us messages via the post message API. The attacker can navigate our window to an evil site. The attacker can even look at the number of the iframes that we have in our window, which is very surprising because I wouldn't have expected as a developer that someone can just open my site and count how many iframes are in there, and the browser does nothing to protect our application from this kind of tampering by another site. So clearly, this can lead to an information leak. So what we can do to fix this is if you set the cross-origin opener policy on your site to either same origin or same site, depending on whether you want it to be stricter or a little more relaxed for backwards compatibility, and that will break the link from the attacker's window to your window. So the attacker can still open your application, navigate to it, and create a new window to your app, but they will not be able to interact with it in any way. And if they do, they will just get an exception and your application will be protected. A very nice side effect of this header is that it allows the browser to put your application in its own process. And there are several very damaging classes of attacks based on microarchitectural side channels that allow the attacker to infer some information about your site when the attacker's site and your site share the same operating system process. And by setting that header, you allow the browser to put your application in its own process to further protect it. All right. So this is my last slide, and this is essentially all the information from the past 40 minutes in one slide, and the summary of all the security mechanisms that are very exciting to us as security engineers that let you protect your application from these long-standing, decade-long security problems. So, for a very quick summary, you can set content security policy with nonces to protect from server-side cross-site scripting. You can use trusted types to enforce restrictions on the use of dangerous JavaScript APIs and make sure that they are safe because they get the trusted type object. You can use fetch metadata request headers to reject requests that are coming from other sites to your application, and you can set the cross-origin opener policy to break window references from untrusted windows to your site. And if you do this, you will protect your application against the majority of the web security flaws that we've seen so far. So we're very excited about using them, and I hope you will consider them for your applications, especially for new applications, because this is a very taken together, they give you very strong security guarantees. So thank you very much. And I'm pretty sure I've run out of time, so if anyone has any questions, I'll stick around here until we'll go to the keynote. So sorry about that, but I'll be here. Thanks.